Hi, I'm Pavel Vargouchik, and together with my supervisor Lukáš Holík, we are working with Symbolic alternating finite automata, trying to make their emptiness testing faster. In the background you can see our actual work, from which today I'm going to talk about our discoveries in preprocessing of automata. Symbolic alternating finite automata have been successfully used recently in string reasoning, where we are interested especially in verification of string manipulating programs. The alternating automata compose better than deterministic or non-deterministic ones. For example, language intersection and complement are performed in linear time. The symbolic part of their definition offers briefer representation if working with large alphabets. But this brevity comes with a cost. Checking their language emptiness, which is the most common question in formal verification, is p-space complete in theory. Luckily, emptiness of many instances that are generated from practical problems can be checked quite fast with an appropriate algorithm. Our goal is to make the checking faster to enable new applications of the automata. Let's introduce them. An automaton has a set of states. One is marked as initial and some are marked as final. There's a set of symbolic Boolean variables. The symbols of input words will be evaluations of these variables. Here we have two variables, v1 and v2. So an input word contains one of their four valuations at each position. The last piece of an automaton is its transition function, which assigns a transition formula to each state. The automaton consumes symbols of the input word one by one and transitions between its configurations, where a configuration is a subset of states. If a state is in the current configuration, its transition formula both constrains acceptable symbols and forces some of the states to be included in the next configuration. Let's see the automaton in action, accepting the given input word. The initial configuration contains the initial state. Its transition formula says that the variable v1 must be set in the first symbol, which is true. It also forces the state q4 to be in the next configuration, as well as one of the states q2 or q3. We'll go on with q2. The next symbol must and must not contain v1, which is impossible. So let's rewind and pick the state q3 for the second configuration. The variable v1 must be set and the v2 must be unset in the second symbol, which is true. We end up in a configuration which does contain only final states, so the input word is accepted. If an automaton doesn't accept any word, its language is empty, which is the property of our interest. Now, let's proceed to our simplification method. Firstly, the presence of final states would unnecessarily complicate our simplification algorithms, and we present a way to get rid of them in our paper, using an additional synchronization variable vf. I will not go into further detail on this, but we can assume there are no final states and the automata accept only in the empty configuration. An important part of our simplification procedure is what we call basic simplification, which uses well-known Boolean laws, structural hashing, and some other common sense. We can easily see that the language of the state q5 is empty, and it can be therefore replaced with Boolean 0. 0 is the identity of disjunction, so it can be removed. The states q6 and q7 share the transition formula. They can be merged into one. There are another two structurally equivalent node, let's merge them together. Now the Boolean law of absorption can be applied. If no other law can be applied from our arsenal, which is fully listed in our paper, we are done with basic simplification. Even for the basic simplification, idea of which is not really new or breathtaking, we have observed very positive impact of our implementation on the overall emptiness checking time. Now let's say a few words about the benchmarking. We have employed a number of model checking tools and algorithms to decide the emptiness of automata generated from practical as well as artificial problems. We have run each tool on each benchmark instance and measured the running time. Then we have run our preprocessing and then the model checking tool again on each instance and measured the overall time. We have then compared the two times. The scatter plots in this slide are generated from a mix of practical and artificial random benchmarks. The practical ones are obtained from email filtering using regular expressions. Whenever a new filter is added, it can be conveniently checked via Automata whether it actually brings something new to the language or whether it is subsumed by filters that are already present. This benchmark has been previously used by Loris D'Antoni and Zachary Kincaid in their paper. Interestingly enough, our implementation of basic simplification was beneficial even for the ABC tool, which implements a form of basic simplification itself. You can see that the times without our preprocessing, which are on the x-axis, are mostly bigger than the ones on the y-axis, where our preprocessing has been used. That's good. Our basic simplification is successful but still a common sense. Our most notable contributions are upshifting and downshifting procedures, which can further turn the automaton that we were simplifying lately into such a simplistic beauty. And all of that in a worst case quadratic but practically linear time. Before describing their ideas, let me show you a little more motivation for them. This is an artificial parametric benchmark which grows with its modulo parameter that can be seen on the x-axis. Overall emptiness checking time grows with modulo much more quickly if only basic simplification is applied. Using up and down shifting in the preprocessing has a highly positive impact on emptiness checking performance. These are the email filtering benchmarks. On the x-axis, there is the time of the best model checking tool if only basic preprocessing has been applied to the automata. The y-axis shows mostly much lower times, which are the times of the best model checking tool plus up and down shifting time if the up shifting or both the up and down shifting procedures have been applied. The color of each dot shows the model checking tool which performed the best. So, our conclusion is that for the email filtering benchmarks, basic preprocessing plus upshifting plus anti-chain model checking is the best combination and is significantly much better than any combination without up or down shifting. The idea behind upshifting stems from the standard determinisation procedure for alternating automata. A conjunction of two states of an alternating finite automaton would be determinized into a single deterministic state. A conjunction represents an intersection of languages. The language of the deterministic state is an intersection of the languages of the two original states. Therefore, it transitions into a conjunction of the transition formula of the two states. you can see that we have shifted the two states Q2 and Q3 above the conjunction, forming a new compound state Q4. Upshifting works not only for the conjunction, but for any formula that contains only states and no symbolic constraints. We call such formula pure. But it doesn't work for impure formula, as shown in this example. Upshifting is impossible in this setting. If we upshifted the two states Q2 and Q3 about the impure formula, we would shift checking of the constraint V1 from the first input symbol to the second one, creating an automaton with an empty language from a non-empty one. The symbolic constraints V1 and not V1 are unsatisfiable at once. However, we propose few simple purification rules that can sometimes transform an impure formula to a logically equivalent one, part of which is pure and can be upshifted. In basic simplification, we were using only rules that shrink the automaton. Upshifting is less conservative, and therefore we cannot apply it wherever possible. It could lead to non-termination if cycles are present in the automaton. Let's analyze the example from left to right. The conjunction is clearly a pure formula. It contains only states. We upshift the states Q1 and Q2 into a compound state Q3 that transitions into a conjunction of the transition formula of the original two states. Q1 was transitioning into Q2, so the first argument of the new conjunction is Q2. Q2 was transitioning into the conjunction, which is now upshifted into Q3, so the second argument of the new conjunction is Q3. We can repeat this for the new conjunction, and so on. Luckily, we have found a heuristic that avoids such infinite looping, but still enables using some upshifting in cycles of the automaton. Before any upshifting, a depth-first search is performed on the automaton. Back edges of the depth-first search are marked. Then we pose an additional restriction on upshifting a node. It can be upshifted only if there is a path without a back edge from the node into any state. Here we can see that all paths from the disjunction to states have a back edge, so its upshifting is forbidden. Then there is a downshifting procedure, a less successful sibling of upshifting. It is used to reduce the number of states. A single downshifting operation is exactly the opposite to a single upshifting. While upshifting is applied almost wherever possible, we precede downshifting by an analysis based on minimum cuts, which precisely determines the nodes on which downshifting will be applied in order to find a good local optimum of the resulting number of states. It therefore never increases the number of states, in contrast with upshifting. The example shows how beneficial can the downshifting be in theory. Our benchmarks, however, indicate that it is only slightly beneficial for the IC3 model checking and severely devastating for the anti-chain's performance. Our implementation and benchmarks are published on GitHub. As for the future work, preprocessing could be certainly investigated further. We have few more ideas, but we have much more promising ideas about specializing model checkers for alternation, so we will follow the potential in that direction in the near future. Thank you for your attention.